All right, so we're going to be going through some example problems together. Normally you would see these on the chalkboard, and so we've got a whiteboard to be able to go through each one of these. What I would really recommend is that if you can, if you've got time, try to pause the video once things are starting to make sense and see if you can finish the problem on your own. That way, if things are making sense to you, then you can just watch the rest of the video to see if what you did was correct. If things aren't making sense, then watch through these whole videos, maybe more than once, and make sure that each one of the steps, you understand why we did each of those steps along with what specifically we were doing. But the why is the most important part of these examples. So the first example we have, if we look at the picture, it looks kind of like a Chapter 2 falling objects problem. We're going to drop a ball from rest, so it's going to fall with an initial velocity of 0, and our goal is to figure out what's going on for it to be able to hit the ground moving at 20 meters per second. So we can start out by drawing a picture of the situation. So we have a building, we have the ball, the initial speed is 0, and we know that at the ground it's moving at 20 meters per second. So for this problem then, for all of the energy problems that we do, the first thing is to identify what we mean by the start of the problem. In this case, the start of the problem before is when we've dropped it at rest, and the end of the problem, or the after, is when it's hitting the ground at 20 meters per second. Now, for all of the energy problems that we do, we really want to be asking ourselves the same general set of questions every time. So for the before situation and the after situation, we want to find out what kind of energy we have. So one of the possible energies that we can have is kinetic energy. And to figure out if we have that or not, we simply have to ask ourselves the question, is the object moving? Is it moving at the start of the problem? If the answer is no, we can just indicate that it's not, 0. And we ask ourselves, is it moving at the end of the problem? If the answer is yes, the useful thing to do before we plug in any numbers is simply to write down 1/2 mv squared. Because from our regular lecture video and from our equation sheet, we figure out that kinetic energy, the term given to us, is 1/2 mv squared. And we have the derivation on a handout as well. Then the other type of energy that we can look for is potential energy from gravity. And for that one, we simply ask ourselves, is the object higher than it is at other points in the problem? At the beginning of the problem, the object is higher than it will be later in the problem, so we can write mgh. And at the end of the problem, the object is lower, and so we write 0. Now, we haven't talked yet, by the time we're seeing this example, where it fits in with our lecture, we haven't talked about any other types of energy, but there could be other questions that we're asking ourselves later, such as if there are springs involved. That's going to be a later part of the problem, but there's no springs here, so we don't have to worry about that. And then separate from before or after, because it is not a term that shows up in energy before or in energy after. It's its own term. We ask ourselves if there is a work term. And that question is simply a yes or no question. So if we reread through the problem here, a 200-gram ball is dropped from a 50-meter tall building. Air resistance acts on it as it falls, and it hits the ground at 20 meters per second. Air resistance, once we start to see these problems more and more, we'll recognize that air resistance is an external force that is acting on this object that isn't already accounted for through the gravity example. And so it will cause a work term. We say yes. Now the key thing here is that the reason that we ask ourselves all of these questions is so that we know right away how to set up the problem, because in general, every single time, our Chapter 7 problem starts the same way once we get to the equation. It will start with energy before plus work added equals energy after. This is kind of like a accounting problem. We figure out how much energy we have at the start of the month. We figure out if there's energy coming into the system or leaving it. And then we find out how much energy we have at the end of the month. Only in this case, it's just the problem that we're looking at. So all of this happens just by reading the setup of the problem. Even before we're asked what to do, and even almost it should be done before we really look at the numbers that we're given in the problem. But once we look at part A, we're trying to find the work done by air resistance. So that lets us know that if we weren't quite sure about that question being yes or no, we can feel pretty confident that it's a yes now. The other thing worth noting is we can make a list of the numbers we were given. So the mass was 200 grams. But we know our standard unit of mass is the kilogram. So we have to divide by 1,000 grams in each kilogram. And so we get 0.2 kilograms for the mass. We already have our final velocity here in the problem, so we can just label that as V. The ball was dropped from a 50-meter tall building, and so that is our height, 50 meters. That's height. But if we think about the fact that air resistance is acting here, air resistance, we may start to notice that the height of 50 meters is also going to be the distance that the ball drops when we start to worry about that work term. But in part A, we don't have to break that work term into any smaller pieces. So when we look at our list here, we take everything in the before column. Then if we said yes to work added, the easiest thing to do is just to write the word work. We don't want to worry about anything beyond what that idea of work is going to be yet. And then we look at our after column. We write down everything in that one too. And certainly, you don't have to write out all of the zeros, but it's actually a really good habit to get into to make sure that you realize that every single time we are looking for every single type of energy. So now we can plug in the numbers that we have. So I'm just going to start to use purple for the rest of this. So 0, we can ignore. The mass here is 0.2. times 9.8 times 50 plus work, because that's the thing that we're trying to find. And then we have 1/2 times 0.2 times our 20 squared. Okay. So we will plug all those numbers in, and then we'll solve for work. All right. So when we get our calculator out, we can just plug all of that in, and we'll get 98 plus work equals, we plug all that in, and we get 40. So to get work by itself, we just subtract 98 from both sides. And we get, as our answer to part A, that work equals negative 58 joules. Now we can do a check real quick to make sure that that negative number makes sense to us. Air resistance is slowing down the ball as it falls more than if it were just falling with only gravity acting on it. So it is taking energy out of the system, and so we did expect a negative term. The air resistance is acting against the motion. So that's our answer to part A. And then so I don't go too low on the screen, I am going to erase this, this that we have here. Okay. Now I know not to use that marker anymore. All right, and so part B is asking us to think about if the force is roughly constant, because the way the air resistance is really going to act, it won't perfectly be constant, but if we just simplify it and look for the average force, or if we just assume the force is constant, we want to find out what that force would be. So now we go back to what work really means from the very first lecture video, where work is either F times D times cosine theta, or in a better, more complete concept kind of way, it's the force in the direction of motion times the distance that we fell. Now, that work term is going to be negative 58. The force that we're looking for is our unknown, so we can just write F. And then the distance from where we started and called before to where we ended and called after, although we called that height before, we can also call it the distance D. The height of the building is the same number value, 50, as the distance that force was acting, so times 50. So to get the force, we just divide both sides by 50. And so we'll get a little bit more than 1. We'll get negative 1.16 newtons is the force. And I should clarify, that force is opposite the motion, and so the negative number of the force, the amount, is what we're getting here. And so we end up with a value of 1.16 newtons acting against the motion. We can also get that negative number by thinking about the cosine of the angle, where if air resistance is pointing up and the ball is falling down, the angle between those two numbers would be 180 degrees. And the cosine of 180 degrees is equal to negative 1. So that problem is fully finished. Again, you can always rewatch the video if you need to for clarification. You can pause and rewind, whatever you need to do to make sure that this example makes sense to you. All right, I'll see you for the next one.